Welcome to Lecture 28, 5.1, Systems of Linear Equations in Two Variables. Alright, this is something we have looked at slightly, but we're going to look at it a little more. So recall, in Chapter 2, we learned how to solve a linear system by graphing. The possible solutions were, well, let's take a look. There was a possible solution of one solution. So if you went ahead and graphed two lines, maybe an example of what type of a solution you might get is they intersect at one point, xy. And the answer for this would be xy, that single point. What was another type of solution? Well, there was no solution. How's that possible? Well, these are two lines that would have the exact same slope. They both continually be moving or rising the same pace and running the same pace, so they would never actually end up meeting. So what would we write for our answer? We would just write no solution. And then there was one more. This is infinitely many solutions. So this is if we had two lines that actually ended up being the exact same line. Okay, so we would write infinitely many solutions. This would be same line. So now I have a question. We already learned how to graph these and find the answer. So what's the problem? Why do we need to learn other methods? Well, here's a question. What's the problem with graphing to find the solution? Well, let's just say I had a graph, right? And we found out that when we graphed, my answer ended up being somewhere that I couldn't find a perfect value for. If this was 1 and that was 1, I know this point would be 1, 1, but that's not my solution. My solution's somewhere in there, some random small decimal. And if we're trying to do any sort of like engineering or any real-world applications with these, most of the time we don't want to, well, I think it's a little smaller than 1, right? We want something, a better approximation. So graphing ends up not really helping us if we start getting some sort of a decimal answer. And this is where algebra comes in. So the problem with graphing is it's hard to find the answer if it doesn't graph perfectly. And I'm going to do perfectly in quotations, because that's just some sort of slang technically. So because of this, we are going to learn two more methods for solving that give exact answers. Okay? So when we're graphing, we can't always find an exact answer. So first method is solving linear systems of equations by substitution. And it pretty much is like how it sounds. You're going to be substituting. So what are the steps for using substitution? First, you're going to isolate one variable in one of the equations. And remember, we're working with two different equations. Second step, we're going to substitute, hence the name, the expression from step 1 into the second equation. So if we had a first equation and then second, we'll take the first one, sub it into the second. We'll solve. Then, step 4, we're going to substitute the newly found variable, which we just found from step 3. We'll sub that into the equation from step 1 and solve for the last variable. And then we'll answer as an ordered pair, xy, if the answer is an ordered pair. You might end up with no solution or infinitely many. Now let's take a look at an example. So solve the following system using substitution. Well, what's the first step? First step is to isolate one variable in the equation. You could do it with either one. Usually, my process is to look for the variable that has the smallest number next to it. Which one has the smallest number? Well, it looks like the bottom equation for the x, so I'm going to go ahead and solve for that one. That's usually my method. So I'll go ahead and do that. I'll take this one, and we'll solve. So we get x equals 6 plus 3y. And then what do we do with that? Well, it says substitute that into the other equation. So what is this saying? This is saying that x, if we ever see x anywhere, we know it equals 6 plus 3y. So let me go ahead and rewrite the second equation. So 3x minus 4y equals 5. Is there an x in this equation? The answer is yes, right there. In order to solve, we want one variable in an equation, and right now we have two. We have an x and we have a y. We don't want those two, we only want one. So to solve that problem, we're going to go ahead and substitute this equation right here in. How do we do that? Well, notice x is supposed to equal 6 plus 3y. So we'll go ahead and just substitute that for the x value. So this is going to be 3 times 6 plus 3y. We just went ahead and substituted that in. Then minus the 4y equals 5. And notice, hey, what do you know? We now have an equation in only y, which means it's easy to solve. So go ahead, distribute that 3 in. We get 18 plus 9y minus 4y equals 5. 18 plus 5y equals 5. And then subtracting 18 from both sides, we get 5y equals negative 13. And then going ahead and dividing both sides by 5, we get y equals negative 13 divided by 5. All right, so we have two options. One, well, we've already found y, right? So now we need to find x. You could go back and resubstitute the other equation, but we're going to go ahead and keep with the course that we have. So we're going to take this y value and now substitute this into the other equation, which we have right there, x equals 6 plus 3y, and now we're going to find x. And to do that, we'll substitute y equals negative 13 over 5 into there. So x equals 6 plus 3 times the negative 13 over 5. And simplifying that out, x is going to equal 6 plus, and that looks like a negative 39 over 5. And that'll simplify out to, if we plug that into our calculator, negative 1.8. Now remember, this is a system, so our answer should be in the point form, coordinate notation. So negative 13 over 5. And negative 13 over 5 is actually the same as a negative 2.6. So I'll go ahead and change that, might as well, to a decimal, so negative 2.6. And there we have our answer. Once again, you should answer in coordinate form. Now the next method we have is solving systems of linear equations by elimination. Some books like to call this the addition method. I tend to use the term elimination, as that's kind of how I was taught. So steps for solving a linear system using elimination. Once again, this is a different method. So we've had graphing as one method, then we've had substitution, and now we're looking at elimination. All three methods you can use to solve, but which one is easier does often depend on your equation. But let's take a look at addition method, or elimination method. So first we're going to write both equations in ax plus by equals c form. Basically, get the variables on one side. Simplify both equations if possible. Then we're going to choose one variable to eliminate. Okay? And note, this is the variable that we'll be canceling, hence eliminate. Step 4. We're going to multiply both equations by a number that will make the same number in front of the variable you have chosen in step 3. If these steps are getting a little too much, just go ahead, hang in there until we get to the actual problem. Normally, a sample or an example helps me understand these better. Step 5. Add or subtract the equations as needed to cancel out the variable. 6. Solve for the variable. And notice, this is the first variable we've solved for. We still need to solve for one more. With the first solved variable, substitute it into the second equation to solve for the second variable. Okay, let's go ahead and put this in action. So first, what is our first step? Well, we have solved the following system using the elimination method, so notice you're told which method to use. This is not always going to happen on an exam. Sometimes it's up to you to decide which method is best. If I don't state a method, you can use any method you want, either graphing, substitution, or elimination. However, if a method is stated, you need to use that method to solve. If you use a different method to solve, you will not receive all of the points, so please be careful, read the directions. Alright, so the first step in elimination is we want to make sure these are in x, y form. So let's go ahead. In the first equation, that is already in xy form. So we have 4x minus 18y equals 2. The bottom equation, we need to move that y over. So we'll go ahead and add y to both sides. And we'll get 3x plus 2y equals 17. The next step is to simplify both equations if possible. Well, when I look at the top one, I have a 4, an 18, and a 2. Those are all divisible by 2. So I'll go ahead, divide by 2. I get 1, 9, and 2. Let's go ahead and write that down, our new simplified version. Once again, note I'm always keeping those braces on the side, because I'm letting people know who are reading this that this is a system. If you might say, well, why do we need to know, why do we have braces to need to know if there's a system? If I took away the braces and you just looked at this, it would look like my equation had gone from this to that. I have no idea how that has been solved. I can't logically figure that out. So to let a person know that these aren't the same equation that we're solving, these are two totally different equations. To let them know this, we use the braces. A lot of the times, it's letting other people understand how you got your answers. Alright, so the top one's been simplified. Can we simplify the bottom one? We have a 3, a 2, and a 17. No, it looks like that's it. Okay, so what is the next step? The next step is to choose one variable to eliminate. Because remember, we want to get down to one equation and solve for one variable. Right now we have 2 variables and 2 equations. Not good. Which variable do we decide to eliminate? That's always a question. Well, my personal opinion is I like to pick the 2 variables that have the smallest numbers total in front of them. So the 9 and the 2 are kind of big, and the x has a 2 and a 3. So you know what? I'm going to choose to eliminate x because there's only a 2 and a 3. Those are smaller numbers. So our plan, eliminate x. Let me go ahead and move this down a teeny bit. Because it was getting a little squishy there. Sorry, give me a sec to just erase away. Alright. Okay, so that's our plan. We're going to be eliminating x. And how do we do that? Well, the next step says multiply both equations by a number that will make the same number in front of the variable. So note, right now, in front of our variable, we have a 2 and a 3. We want them to be the same. So think of a common number that 2 and 3 can both go into. Well, they can both go into 6, right? So we're going to create a 6x. So my goal is to end up with a 6x for the first equation and a 6x for the second. How will I accomplish that? For the first equation, we're going to need to multiply all of them by 3. Please note, you need to multiply everyone by 3. You can't just be choosy and multiply the 2 by 3. This is the property for equations, remember? Alright. So once I do that, I get the 6x, but I have that 9 times 3, so that'll be negative 27y equals, and then that 3 times 1. So 3. Okay, awesome. Our goal is done for the first equation. We have a 6x. Now, we need to figure out how to get a 6x for the bottom. Well, to get 6 from 3, we'll just multiply by 2. And we multiply the side by 2 as well. Alright, working that out, we get 6x plus 4y equals, and that looks like it's going to be 34. Has our plan been accomplished? Yes, it has. We have created 6x. Alright, so what's great about making the same number? Well, for step 5, we're going to add or subtract to cancel. Is that really possible? Let's take a look. Well, we had two options, addition or subtraction. And what do I mean? Well, if I chose to do addition, what I'm saying is I want 6x plus 6x. But that would give me 12x. And remember, my goal was to cancel 6x. Okay, it didn't work. We didn't cancel the x's. Next plan. So since addition's not going to work, the only other option we have is subtraction. Let's go ahead and do some subtraction and see if that works. Well, 6x minus 6x, hey, that cancels. The x's are gone. Awesome. Our plan is going forward perfectly. Now let's keep going. We have negative 27y minus 4y. Let's write that on the side. Negative 27 minus 4y. Well, that'll end up giving us, let's see, 31. So we have 31y. It's a negative 31, by the way. And then we have 3 minus 34. As always, I write it on the side. If you can do it in your head, awesome. If not, writing it out on the side is really helpful, okay? So don't worry about showing a little scratch work. As always, though, unless you erase it, please write scratch work on your exam. Once again, scratch work is not the important work that you're showing in the actual solving. Okay, this work right here, that I wouldn't consider scratch work because that is important in the solving, and that's something that I'll be looking for grading. Scratch work is usually just the small little sort of side sketchings, okay? So sometimes I've noticed on the exams, some students are sort of canceling out their main work and calling it scratch work. That's not normally done. Normally you just do the small sort of little checkings and guessings as your scratch work. Once again, unless you erase it, make sure to label it as scratch work. Alright, so we have 3 minus 34. That looks like it's going to end up being negative 31. Hey, what do you know? We get 31 on both sides. Go ahead and divide by 31. And we have that y is equal to 1. Awesome. But we're not done. Remember, we still need to solve for x. So to solve for x, we can choose either one of these equations to solve. Either the top one or the bottom one. Now, which one would I choose? Well, usually I'll try and choose the one that either has the variable isolated already or the smallest numbers. Now, the bottom one has x almost isolated already, so I'm going to go ahead and choose that. You could choose the top one. So now we're going to find x. I chose the bottom equation. Once again, you could choose either one. Alrighty, and then, so y is equal to 1. We'll go ahead, plug that into our equation for solving. We get 3x equals 17 minus 2 times that 1. Then 3x equals 17 minus 2. And let's go ahead and keep solving. Dividing both sides by 3 to get x by itself. Ooh, and we have x is 5. But once again, we need to answer in coordinate form. X, y, which would give me 5, 1. Once again, the order is important. Always your x value first, and then your y value after. Alphabetical order. Okay, so hopefully that wasn't too bad. Now let's see. I have a question. Which method is better or easier to use, elimination or substitution? And my answer, it depends. What do you mean it depends? Well, it depends on the way the equations are given. If they're already all set up, so we have an x, y equal to a number, and an x, y equal to a number, then usually I'll choose to do elimination. However, if it's set up so we have one variable already equal to itself, then oftentimes I might think of doing substitution. So if you're given a choice, just think about the way the equations are set up and what kind of numbers you're working with, and then make a, maybe an educated guess on which one works. But if you're not given a choice and you're told which method to use, remember you need to use the method given. All right. So now, we're moving on into systems of linear equations in applications. All right, remember, just a little reminder here, what steps do you need to show for application and word problems? Now, these are the steps that I look for in grade 4. Okay? So you need to give me a let statement. What is this? This is where you introduce your variable. Now remember, we are in an algebra class, so algebra should be part of your solving. If you manage to solve a word problem without using any algebra, and you give me your answer, that's awesome. You get a point for the answer. The thing is, though, remember, this is an algebra course, so I need to see algebraic work. So usually, more points come from actually showing the algebra. So oftentimes I tell students, if you can solve it on the side without algebra, go ahead and do that first so you know the answer, and then work your way backwards and work on the algebra. It's good if you already know how to do the algebra, but if you're struggling, sometimes it helps to just take a look at the problem through a non-algebraic eye and try find the solution. That does work for some students. So after the statement, second, you're going to do your equation. After that, you're going to solve the equation, and lastly, you're going to answer in word form. And one thing to note, for 2x2 linear systems, there are 2 unknowns in the problem. So oftentimes when you're reading a problem and there are 2 unknowns, you might be working with a system. So one thing to note, though, if you're told to use a system, you need to use a system to solve. If you're not told to use a system, and you use a system, that's okay. Unless you're told, don't use a system. Once again, it depends on the directions. So example 3. How many ounces of 20% and 35% acid solution should be mixed to produce 15 ounces of 30% acid solution? Let's draw a visual here. So let's see. We have some sort of a solution bottle. We're adding to it some other sort of a solution bottle. And we want to get a final amount, right? That's just sort of the visual of what's going on here. So one thing to note, if you have a chart or a diagram, you don't actually have to write let for your let statement, as long as you draw it in and it makes sense visually. Now what are we working with here? Well, we're working with a 20% and a 35% solution that we are adding them together. So I'm going to go ahead and draw those in. So let's see, we have 20% being added to a 30%. And what do we want to end up? Well, we want to end up with 30%. Okay, whenever we're working with mixture problems, these are called mixture problems, we always have the percentage and then we have the amount on the top. After that, we'll end up multiplying them together to get our equation. Well, with the 20%, how many ounces do we have? We don't know. That's actually what it's asking us. It's asking how many ounces of the 20 and 35%. We don't know either amount. Well, since we don't know either amount, those can be our variables, right? Why not? We can say let x be the amount for the 20%, and why not say y be the amount for 30%? Sounds good. And then it tells us we want to produce 15 ounces. Okay, they gave us that. That's good. So we have a small problem here, though. Because I use 2 variables, I need to use 2 equations to solve. And right before I get solving, I notice there is a small error here. That should be 30% under the y. Sorry, 35%. All right, so now we can go ahead and create our equations. The first one we can create is, well, we know that we're adding 2 mixtures to get 15, right? That was a simple one. The next we can use the actual normal way we set this up, which is the percent times the number. So it'll be 20 over 100 times x plus 35 over 100 times y equals 15 times the 30 over 100. Alright, so now, what method should I use for solving? I can either use elimination or substitution. Well, since these are already set up in the x plus y form, I'm going to go ahead and use elimination. You could try this with substitution if you wanted. Before we do that, let's go ahead and simplify the bottom equation. Let's get rid of those hundreds. Always simplify in math if you can. So if x plus y equals 15, 20x plus 35y equals 15 times 30. You know what? That bottom equation looks like it can still be simplified. I think we can divide everything by 5. Let's go ahead and do that as well. So dividing by 5, we'll end up with, that cancels, we get a 6, we get 7 there, and then we get 4. Then we have x plus y equals 15, 4x plus 7y equals 15 times 6. What is 15 times 6? 90. Let me check that one more time. Awesome, 90. All right. Now we have them perfectly set up for elimination. We have x's lined up and the y's lined up. The plan is, which one should we cancel? As usual, I like to pick the one that has the smallest numbers in front of it, which looks like the x's since it's a 1 and a 4. So we're going to go ahead and cancel x. In order to cancel x, we need to make them the same. Since one of them is already just a 1, let's go ahead and make them both a 4x. Did you guess that? Hopefully. Alrighty. In order to make them both a 4x, I'm going to go ahead and multiply the top one by 4. Then I have 4x plus 4y equals, what is 15 times 4? I think that's 60. Let me check with my calculator. Yep, 60. And then 4x plus 7y equals 90. Alright, we're going to go ahead and either add or subtract these. Since they're both positive 4x's, I'm going to go ahead and do the subtraction. So 4x minus 4x, that cancels, and we're just left with 0x. Then we have 4y minus 7y. That'll be negative 3y. And then, what do we have next? 60 minus 90. That'll be negative 30. Which means, if I can squish this in here, y equals 10. Alright, y equals 10. Awesome. We're halfway there, guys. We just managed to solve for one. So how do we solve for the next one? Well, to find x, we're going to go ahead and use one of the original equations and substitute 10 into it. So if you're feeling adventurous, you could go ahead and substitute x into this nice big equation with all the fractions, but I'm not feeling quite that adventurous this evening or day, whichever time it is where you are. I'm going to go ahead and use the nice x plus y equals 15. Well, we know that y equals 10, so we're going to go ahead and substitute that into the equation. So x equals, x plus y, which is 10, equals 15. Then we'll go ahead and subtract 10 from both sides, and we get x equals 5. Well, what's my solution? Do we just do our little 5, 10 and move on? The answer is no. Remember, this is a word problem. We need to answer in word form. What do the variables stand for? Well, let's take a look. The x is the 20%, and the y is the 35%. X is 20%, y is 35. Let's go ahead and write that down. So we need, we need 5 ounces of the 20% solution and 10 ounces of the 35% solution. Period. Awesome. All right. Hopefully that wasn't too bad. Now let's take a look at another problem. So another systems. Kelly runs a small booth at the Kailua Farmers Market and sells boba tea. The regular size sells for $2.50 and the large sells for $3. Last Thursday, she made $67.50 from selling the 25 boba drinks. How many drinks of each size did Kelly sell? Well, we can't really do much of a diagram for this one, so we're going to go ahead and do a regular let statement. What are we trying to find out? We're trying to figure out how many drinks of each size she sold. And how many sizes does she have? She has a regular size and a large. So we have two variables. Awesome. Well, let's say let R equal the regular size, and let L equal the large size. You could use X and Y if you want to. I just thought I'd make things a little more fun, you know? Alright, now let's see. We're going to go ahead and set up the equations. Once again, two variables means we need two equations. Usually, you'll create equations either in terms of maybe miles per hour, dollars, numbers, percentage. Usually, you pick things that have the same unit to create your equation. So what are the different units I see in this problem? Well, one of the first units that stands out to me is money. We have $3, $67.50, and $2.50. I know I can create an equation using money. Well, if she sells, or she made $67.50, right? How can we make that into an equation? Well, let's back this up real quick. If you told me that you made $15, so let's say you told me I made $15 last week, and I sell my drinks for $5 each, how many drinks did you sell? Well, you made a total of $15. Each drink sells for $5. That must mean you sold 3 drinks, right? In order to get the $15. Well, that was the thing we were trying to figure out, right? How many you sold. In this case, we don't actually know how many she sold of each size. We only know that it's R or L. But we do know the dollar amount she sold for each one. So to find that, we're going to go ahead and write, let's see, the regular size was R. So R times 250. Actually, let me rewrite that as 250R plus the largest she sold, so L, is going to equal 67.50. Now, what other equation can we make? Well, what other information have we not used yet? Well, we haven't used that she sold 25 boba drinks. Well, that basically means that the number of regulars she sold plus the number of larges she sold should equal 25. And there we go. We've created one equation in terms of dollars and the other in terms of just regular old numbers. So that's one way that I find it's helpful to create the two equations. Look for the different units in your problem. Alright, so since we solved the other equation using elimination, I'm going to go ahead and solve this one using substitution. So to solve it using substitution, first, what should we do? Let's go ahead and change the bottom one for substitution. Why? Because it has the smallest numbers. I'll go ahead and solve that for R. Why R? I just felt like choosing R. And then we'll go ahead and substitute this, R equals 25 minus L, into the first equation. So we're substituting R to find L. So we get 250, and this time we're substituting that in. So 25 minus L plus 3L equals 67.50. How do you know if you did the substitution correctly? Well, if you have only one variable in your equation, notice we now only have L, so we've succeeded. All right, let's go ahead and distribute that 250 in. So 250 times 25 is 62.5. And then minus 25L. I'm just going to go ahead and drop the 0. Now, how do we simplify this? Well, let's go ahead and combine the like terms of the L's. So that'll be 3 minus the 2.5, which is just 0.5. Let me pick a different pen. So 2.5. Gotta be careful here with all the decimals sort of disappearing. And then we're going to subtract the 62.5 from both sides. So you have 67.5 minus the 62.5, and that is 5. And lastly, let's divide by 0.5. So 5 divided by 0.5 is 10. Awesome. L is 10. Remember, L was the number of large drinks, so she sold 10. All right, but now we need to figure out the number of regulars she sold. So how do we do that? Well, let's use this original equation here. So we're going to find R. It's always good to label your work. So R is 25 minus L, and we found L. L is 10. We'll go ahead and substitute that into the equation. And then we have R equals 25 minus 10. R equals, so 25 minus 10 is going to be 15. But remember, this is a word problem. We're not just going to answer in a coordinate form. What do R and L stand for? R and L stand for the regular and large. So my answer is going to be, who is this? Kelly? Yeah, Kelly. Kelly sold 15 regular drinks and 10 large drinks. Period. Alrighty, that is it for this section. Please email me if you have any questions.